Hello everyone, welcome back. We're going to start a new chapter on elimination reaction. This is a continuation of what we had for substitution reaction. In substitution reaction, if you remember, we have an alkyl halide which has a living group, and also we used a nucleophile. In this case, for the elimination, we need some kind of base, which are also nucleophiles in the substitution reaction. So this is a new mechanism. Sometimes it has some resemblance with substitution reaction. So we're going to devote the whole series of videos on elimination reaction. So this is a continuation from another chapter, which is a substitution reaction. Now we're going to study elimination reactions of E1 and E2 type. So for that you need a base, a strong base in most cases, and an alkyl halide, which you have seen in the substitution reactions. The general scheme for elimination reactions is shown here. You have an alkyl halide which has this leaving group X, and the designation where you have the leaving group is an alpha carbon, and the base would attack or abstract the proton or the hydrogen. You need always a beta hydrogen for that reaction to work. So that's called beta carbon. Beta and alpha. Alpha contains the leaving group, and beta contains always at least one hydrogen for elimination to happen. So the base comes, pulls out this proton, and these two pair of electrons would collapse into forming a new bond. So this is the alkene bond, or the alkene product you always get from an elimination reaction. So this is a general reaction scheme where an alpha carbon contains the leaving group, and the beta carbon would have a hydrogen. So this actually is called beta dehalogenation. That means you are eliminating dehydrohalogenation. So dehalogenation or beta hydrodehalogenation. So this is a dehydrohalogenation. Actually, in a better term, it's beta. So the beta hydrogen is the one to be eliminated, and also the halide from the alpha carbon. And as a result, you're making an sp2 carbon. sp2 carbon for a double bond. So all elimination reactions will produce an alkene product. So it's not substitution. You have a base comes in, takes up that hydrogen, that's why it's dehydrogenation, and as it takes that proton, this bond comes in and this leaves. So this will give you an alkene product. For that you need always a strong base. In this case, for example, in a real compound, this is just a general scheme. I'll put this as a general scheme. But here we have a 4 carbon actually. It's a 1-bromobutane compound. If you just look at here, it is 1-bromobutane. So you have all the conditions that are necessary for an elimination reaction. Here you have a hydrogen. One of the two hydrogens is a beta carbon on a beta carbon. This is an alpha carbon. The alpha carbon contains the halide, and the beta carbon contains at least one hydrogen for the elimination to work. Here we have a bulky base. From now on, will introduce, most often I would explain or come up with a term like bulky base. Potassium tertiary butoxide. Potassium tertiary butoxide is a bulky, strong base. So here you need to remember this is a bulky, strong base. We will often use this term, so it's potassium tertiary butoxide, or sometimes we put it as KOTBU. In your text you might find also written as KO tertiary butoxide. So we have a very strong base. We have all set up the alpha carbon has a halogen that would leave, and also the beta carbon has at least this or that hydrogen would be eliminated. So when that makes the elimination reaction, you would form this compound. This compound is now 1, 2, 3, 4. This is a 1-butene ENE, alkene. So remember the naming also. So that's 1-butene that's generated. So this elimination reaction uses alpha halide, and also beta carbon should have at least one hydrogen. Okay, the next example in the elimination reaction, we are using sodium etoxide. It's a strong base. It's not bulky, but somewhat an alkoxide like that, but it is an etoxide. So this is a strong base as well. Strong base, but not as bulky as tertiary butoxide. So this is ethyl. So ethyl is not as bulky as tertiary butyl is much more bulkier. In the future, this has important consequences why we say sometimes bulky, sometimes not bulky, strong base, weak base, because the reaction would be much more influenced by the strength of the base, availability of beta hydrogens, and all that. So this is just introductory to elimination reaction. So I would encourage you to go through the video, each one of the series, so that you would follow all the sequences in terms of as we go along in the elimination reaction schemes. Here you have a strong base. You have at least here or here beta carbons, a beta carbon. This is considered as beta carbon. This is as beta carbon. No, I made a mistake here. No, not that one. This is beta carbon. So this is set up for elimination reaction. Sodium etoxide is a strong base. So whether you do it from here or here, the compound is still the same, cyclohexene. So one of the hydrogens would be abstracted by the base, say this one. Then the bond would form here. The base comes in and takes up that. The chloride leaves. You form a cyclohexene compound. Because hexene, it's not hexane, it is ENE, because that is cyclohexene. So you are forming cyclohexene with elimination reaction. So one hydrogen and one chlorine is eliminated, so that is called dehydrohalogenation. Dehydrohalogenation. The term you should be familiar with now. Dehydro, meaning that hydrogen is being removed, not only hydrogen but chlorine. Therefore this is called dehydrohalogenation reaction. Both the halide and also the hydrogen are eliminated to form an alkene. So this is just a general introduction to elimination reaction. So We'll continue more on in depth with mechanisms, solvents, kind of bases that would be used in these reactions and products. And there are new terms that you'll be learning. There is radioselective and stereoselective reaction. So there are new terms that you'll be learning in the elimination reaction. Radioselectivity and also stereoselectivity are some of them which we're going to study in this series of videos. Looking more in detail with about the bases, what we use in the common basis for elimination reactions could be hydroxide type, such as sodium hydroxide, potassium hydroxide. These are the OH minus containing bases. So they are strong bases, and in elimination reaction we could use either sodium hydroxide, potassium hydroxide. So these are the common bases that are being used. These are hydroxide type. But when the base is formed from an organic compound, especially from organic alcohol, they are called alkoxides, not hydroxide, alkoxide. This is to indicate that they are made of alkyl groups or alcohols. For example, here you see sodium methoxide. I would write here, this is sodium methoxide. So this is designated as sodium NaOCH3, so that's methoxide, sodium methoxide. So the negative charge is on oxygen and the positive charge is on sodium. So sodium is not the one participating in the reaction, rather the methoxide is participating. Here you have sodium ethoxide. You can have potassium ethoxide as well, but here as an example, sodium ethoxide. So it is NaOET. So that's the abbreviation also we use to show sodium ethoxide. Here you have a bulky tertiary butyl methoxide. So this is potassium tertiary methoxide. That is a strong bulky base. These are strong bases, but the bulk increases on when you see in T-butyl group. So these are generally what you'd encounter in solving problems. They could be sodium methoxide, potassium methoxide. It could be any sodium ethoxide, sodium methoxide as well. So, and also in designating alpha and beta carbon, you should always be careful what product you'd get. So let's say we have one of these bases in the reaction. So if you are given this, what are the products of this elimination reaction? Okay, let me designate, this is obviously the alpha carbon, always, because it's containing the halide. And the alpha carbon would be anything one carbon away. Actually, this dehydrohalogenation is called also 1,2 beta elimination. Instead of alpha beta, we could also say 1,2. One being where the halide is, the alpha, and 2 would be the position where the hydrogen is. So now, be careful. In this example, you have 2 positions for the beta hydrogens. One of this can be possible. And also, if you just look at here, one of these hydrogens also could do the reaction. So you would get 2 different compounds in this elimination reaction. So let me do the first one. The first one, by using this, the base comes in. Okay, the base, like sodium methoxide or OMe minus, as an example. The methoxide comes in with a pair of electrons, takes up, abstracts that proton. The terminology is abstract that proton. A base abstracts this acidic proton. And now this becomes here, and this is eliminated. So the product from this mechanism is CH3, CH double bond, CH3. So the alkene is on carbon number 2, plus another one. So there is radioselectivity and stereoselectivity. We'll come up with that one. But I have also beta carbon here. This is also a beta carbon because it's one position, this is two position. So there is also a possibility the base can abstract one of the hydrogens from here. So what happens is, let me write it out in detail. This CH3 can be written as this, CBr, right, and hydrogen, and C, H, H, and CH3. In this case, if we designate this is a possibility, because this is a beta carbon in the upper case, but here now we have a beta carbon right here because it contains hydrogens, and the alpha is here. So the base comes the same way. It abstracts that proton, or that proton for that matter, or this proton. This collapses back, and this leaves. So the product looks like CH2 double bond CH, CH2, CH3. So you get two products. They are different. They are not the same. Actually, they are constitutional isomers because the way they are bonded is not the same, even though they have the same number of carbon. So they are constitutional isomers because this is a 2-butene and this one is a 1-butene because the double bond is at one position. Here the double bond is at carbon number 2. You get two products which are not the same. They are constitutional isomers actually. So you produce constitutional isomers. They are not the same compounds. From one reaction you get mixture of products. So in that reaction path you have two different compounds, a 2-butene and a 1-butene. So if in a question you would be asked, I saw this and this in the reaction mixture, what is the reason? You'd say the abstraction of the beta hydrogen is from this carbon in one case, from this carbon in the top case, but in this case there is a possibility also in the reaction mixture it would abstract beta hydrogen from this carbon. So the presence of two beta carbon possibilities gives you two products, even sometimes 3 or 4 based on how many beta hydrogens there are, how many different beta hydrogens you would have. So that is one thing you need to remember in the elimination reaction. This is just an introductory part of the elimination reaction. We'll go deeper into the details of the mechanism of the reaction, but you should be aware of what those two compounds came from. One is from abstraction of this beta hydrogen, the other is from abstraction of one of the beta hydrogens. So remember, there is an alpha and beta position, or we call it as 1,2 position as well. That's the same. So those would give you different radioisomers. Radioisomer mean the position of the alkene is different from one another. 2-butene is not the same as 1-butene. They are different compounds. They are isomers. They would have different chemical property. They would have different physical property as well. So you are producing different compounds in this case. But in some examples, you may not have that possibility, only maybe one beta carbon and one beta hydrogen. So with this, we'll continue more on the details of the elimination reactions. Let me show you here what this compound, when treated with a base, this is DDT, it's an insecticide. So if you are treating this with a base and you have a halide that could be living, you first identify how many hydrogens are possible in the elimination reaction. This compound has only one beta hydrogen. That beta hydrogen is this right here. So there is no any radioisomer like previous example I showed you that you would have different radioisomers. This is only one beta hydrogen. So if this is an alpha carbon, actually containing more than you need, 3 chlorines, but this is an alpha carbon, this is a beta carbon. So the base would abstract this hydrogen, and the bond would collapse here and forms this product. So the product looks like just only one product, double bond there, and Cl, Cl. So this is an example where you have one sp3 hybridized carbon containing only one hydrogen as a beta hydrogen because it's on a beta carbon, and the elimination reaction happens along this bond, and you're going to form that double bond right there. So this is a double bond you'll be creating. No other beta hydrogens present in this compound. So there are cases where you would have only one hydrogen to eliminate, but in some cases you could have more than 2, 3 beta hydrogens that are possible to eliminate. So make sure that you survey the compound and see what are the potential hydrogens that can be lost during the elimination reaction. So this is a simple reaction where you have only one beta hydrogen on a beta carbon, because this is an alpha carbon containing the halide. Actually, this has more than one. So this DDT is converted by base. Any one of these strong bases would give you an elimination product, just one product. So we'll continue now to understand first in the type of compounds that are formed, which are alkenes, but alkenes have different stabilities, and hybridization is sp2, and we kind of review how sp2 hybrid carbons are formed, and also the stability of each different type of alkenes. So there are monosubstituted alkenes, disubstituted alkenes, and tetrasubstituted and tri-substituted ones. So we're going to study the stability of alkenes. Reason being that based on the stability of those compounds, the kind of product that would be formed is dictated by the stability of the alkene. If the alkene is not more stable, there is a preference to a more stable alkene. Even sometimes the alkene may not form at all because of the stability of the type of alkene you're going to form. So we'll go in detail with the type of alkenes that would be formed, and also the sp2 hybridization. Let's see some of the bonding that an elimination reaction forms. That's an alkene or a carbon-carbon double bond. So the smallest carbon-carbon double bond that you find in chemical compounds is in ethene or ethylene. And if you just look at the hybridization for carbon-carbon double bond, the hybridization is made of sp2 carbons. These are sp2 hybridized carbons. They have 3 lobes at 120 degrees. So all of this with hydrogen, obviously with one is hydrogen, and one is hydrogen. That's the sigma bond. So the sigma framework of this ethylene or alkene in hybridized carbons looks like this. So all of these are sigma bonds. So you have 1 sigma bond, 2, 3, 4, 5 sigma bonds, you can see. So that's how the bonding looks like in ethylene. But don't forget, there is 1 pi bond that's formed from unhybridized p orbital, unhybridized p orbital, that is perfectly at 90 degrees to the plane of the board. If you just take the sp2 orbitals are lying flat on the whiteboard, the p orbitals would be up and down on the plane of the board. So I'll just put them here with this dashed designation. So if you just look at all the sp2s are, for example, flat like this, the p orbitals are here and there. So one unhybridized p orbital from one of the carbons, another one from this. So it will be just perpendicular to the plane of the all sp2s. So these are the p orbitals that makes the pi bond. So the p interaction makes the pi bond. So there is only 1 pi bond and 5 sigma bond. So ethylene or any alkene is made of, at least for this one, 5 sigma bonds and 1 pi orbital, unhybridized. So this is how the bonding looks like in alkenes. The alkyne would have 2 unhybridized p orbitals, therefore it makes the second pi bond to make a triple bond. But now we are just focused on an alkene. These are the hybridizations. So this is a sigma of 1 hydrogen S overlapping with sp2, 1 hydrogen 1s overlapping with sp2, 1s of the hydrogen overlapping with sp2, forming all of the sigmas. And finally here the sp2 sigma bond. So this is also sigma, but this is a pi bond. So this is how the pi bonding in the alkene looks like. One thing you should remember is that due to the presence of the pi bond and the sigma bond across this bond, these are not rotatable. This is not rotatable. You can't rotate across this carbon-carbon. You cannot rotate, for example, holding this and try to rotate. That will break the bond. So there is no rotation across the carbon-carbon bond. So one of the properties is no rotation across the carbon-carbon bond. So that's also one of the properties. Any sigma bond, if you remember in Newman projection, we were able to rotate all the sigma bonds, the carbon-carbon bond. For example, if you have CH3, that means this, all of the sp3 hybrid orbitals, the carbon-carbon bond can freely rotate. This can rotate. This cannot rotate. No rotation for carbon-carbon double bond. It's fixed. And there are some properties of the alkene. For example, here we call this kind of alkene monosubstituted alkene. all of these are hydrogens, the three of them, but only one is alkyl group. It could be CH3, CH2, aromatic ring, or anything that is alkyl is a substitution. So this is only singly substituted. One of them is only substituted. So it's mono-substituted alkene. Mono-substituted alkene. So it's mono-substituted. And this one, if you just look at here, that carbon contains both alkyl groups. So these are hydrogens, but here the two are alkyl groups. It could be the same or it could be different alkyl groups. So this is a di-substituted alkene. In terms of stability, a di-substituted alkene is much more stable than the mono-substituted. We're gonna see that. So this is di-substituted. This you have one alkyl group, three of them. So it's a tri-substituted alkene. Only one of them is a hydrogen. So that's a tri-substituted alkene. Here, when you come to look at this, it's a tetra-substituted or substituted, highly functionalized, because all of them are alkyl groups of different size, or they could be the same. So that's tetra. The most stable alkene would be this. So as you see, the substitution pattern also gives you a property of an alkene which is different from one another. Stability also is different. So the tetra substituted is much greater stable, and the tri substituted is much greater stable than the di, and it goes like this. So ethylene is not substituted at all. Ethylene, the smallest alkene is ethylene. It's not substituted at all. So that is the least stable one. So this is much greater than the ethylene. So stability wise, this is the most stable alkene. Here I have real life examples of compound. This is cyclohexene. This is called cyclohexene. Remember the ENE for alkene. So this is a di-substituted because this is an alkyl group, because it's CH2 here, CH2 here, but these two are hydrogens. So this is a di-substituted alkene. So this is di-substituted. Here, this alkenes are different substitution pattern. For example, if you just look at this one right here, this is tetra-substituted alkene. The internal within the cyclohexene ring is a tetra-substituted one. One alkyl here, one alkyl here, one alkyl here, one alkyl here across that double bond. So it is tetra-substituted. If you just look at this alkyl, there is an alkyl here, and there is an alkyl here. So this is a di-substituted. If you just look at this alkene right here, it has one alkene here, another alkyl here, another alkyl, which is a metal group here, but only one hydrogen here. So this is a tri-substituted alkene. That's a tri. This is vitamin A, by the way. This is a molecule highly functionalized with alkenes. So vitamin A is mostly non-polar, and it dissolves mostly in fats. So vitamin A is more soluble in fats than in water. If you just take a tablet of vitamin A, it's more bioavailable when it's also dissolved in fat. So if you just look at this one, this is a di-substituted. You have one alkyl chain here, another alkyl group here, but the two are hydrogens. So this across this is a di-substituted. This is a tetra-substituted one. Here I have a tri-substituted alkyl, because one alkyl here, one alkyl 2, one metal group here, which is metal here. So these are metal groups, by the way. We don't usually show them. This is CH3. So this is vitamin A. So vitamin A contains a disubstituted, a trisubstituted, and a tetrasubstituted alkene. So the stability of each one of those alkenes depends how they are substituted. So this is a general scheme, or the general properties of alkenes and their functional group. Their functional group is a double bond. So the reactive group in alkene compound is a double bond. The pi bond is that's electron rich. That's why you have reactivity center for any reaction would be the double bond, not the sigma bond. So this overall gives us a product of an elimination reaction. Usually alkenes are formed by an elimination reaction, and you form different kinds of alkenes. So the stability of those alkenes also depend on how the substitution patterns are. And I also covered the hybridization. There is a specific video on hybridizations. You might want to review that part of the lecture. So we'll continue more on elimination. Talking more on the stability of alkenes, here are some examples to demonstrate the stability of alkenes depend also not only in the substitution but in the isomerism that exists. Here, if you just look at both, these are disubstituted alkenes. This is this is disubstituted alkene. But the stability between the cis and the trans, the reason why we call this isomer stereoisomer as cis is in the same phase. The two alkyl groups are on the same phase. So CH3, CH3 are on the same phase, on the top, and the two hydrogens are down. So this is a cis isomer. Here the metal groups are, one is in the upper, between these two it's on the top, between these two it is down. So they are in opposite. So this is a trans isomer versus a cis isomer. So both are disubstituted. So which one is more stable? As you know, the cis doesn't convert to trans by itself or by any chemical reaction, because the double bond across the carbon-carbon bond is not like a single bond. It cannot rotate. A single bond like this, a sigma bond, can rotate. But this one does not rotate. So there is no rotation to go to from cis to trans. No rotation possible. So these are clearly two different compounds. They are not the same. They are not interconvertible by rotation. There is no rotation that converts cis into trans. The bond has to be broken. That means it's a different chemical reaction. So they are not the same compounds. So in terms of stability between the cis and trans, the cis always has a more unstable configuration, because if you just look at these two large groups, metal groups, once it goes up like ethyl, propyl, it becomes more severe. So both clash. They would come together and make that kind of clash. So the cis is less stable than the trans. The trans, it's just clashing with a small hydrogen to metal, small hydrogen to metal. So relatively, the trans is more stable in alkenes. Trans alkene is more stable than cis alkene. So the generalization is trans alkenes are more stable than cis alkenes. This is because of sterics. Okay? Steric factor. So we have already said that more substitution make the alkene more stable. The reason why more substitution alkyl groups are stabilizing the double bond is by inductive effect they electron donate to the alkene. So alkyl groups are stabilizing the double bond by giving more electrons. So they are electron donating by inductive effect, electron donating groups. This is also electron donating. So the more it is substituted, the more it is stable. But also, in terms of stability, that cis is not stable because of sterics. So you have to always consider sterics versus how much electron donation is present. Here, this is a di-substituted. Okay, a di-substituted. And here, this is a di-substituted. This is also a di-substituted alkene. Okay. So here, these are terminal alkenes because the hydrogens are at the terminal. So the 1,2 substitution makes it more stable than like this substitution pattern. So internal double bonds are more stable than terminal. This is terminal alkene. Terminal because the terminal point is not substituted. It's hydrogen-hydrogen. So terminal means the one position is just hydrogens. Here the substitution is at 2 position. Here is the substitution at 2 positions. So if we compare the stability of this, the terminal alkene is much less stable, least stable than the internal alkene. Internal because it's in between carbons which are substituted, and here this is less stable than the other because it is cis alkene is less stable than trans alkene. So 2 factors here. This is a less stable, next stable, more stable. So this is stable, most stable. So again, to review this is a terminal alkene. Terminal alkene is like if you have something like this is terminal alkene. But if you have something like this is not, this is internal alkene. Internal. The alkene is between alkyl groups. These are hydrogens. So this is terminal. Terminal alkene is less stable than internal alkene. So the more substituted is a double bond, the more stable. So this is less substituted. That means even though there are 2 alkyl groups, the substitution is not in symmetric pattern. That this is a terminal, very reactive, least stable. Here it is internal, but it has some steric clash between these 2, so cis is not as stable as trans. So this is internal, but these are cis and trans. So that's how you evaluate stability of an alkene. So need to review all what factors actually help stability of an alkene. Here you have a di-substituted alkene, and here you have a tri-substituted. I will add one more actually. If you have something like this is a di-substituted, but this is terminal alkene. Terminal because these are hydrogens. Exocyclic terminal alkene. These are internal alkenes. Internal because this is di-substituted, this is tri-substituted, this is di-substituted, but it's a terminal alkene. So it has both ends have alkyl groups. Both ends have alkyl groups. Here both ends, this is alkyl, but the terminal one has hydrogen. That is the least stable. So in terms of stability, this is the most stable would be this one, most stable, number 1 stable, number 2 stable, least stable is this, number 3. So this is how you would evaluate the stability of an alkene in the formation of alkene products from elimination reaction. So in the next video, we have now covered the introductory part of alkenes, what their properties are, what their stabilities are, and what are the different isomers you could have, cis and trans, and also by electron donating alkyl groups stabilize an alkene group. Internal alkenes are more stable than terminal alkenes. With this, we would transition to studying more on mechanisms of elimination reaction. So like we have studied SN1 and SN2 reaction, we're going to study also E1 and E2 mechanism when a base comes and abstracts a proton and the halide leaves. That is the 1,2 dehydrohalogenation, or an alpha beta dehydrohalogenation reaction is an elimination reaction. We have already covered in this video about bases. You have hydroxide bases and alkoxides and so on. So the next video would be on the mechanisms of elimination reaction E1 and E2.